I woke up at 6:30. And I was like, still at 8 on the field. I went back to sleep, woke up at 8:07. I was like, oh no. I grabbed Chris, I was like,
all right. We're going to go ahead and get started. So I know it's been a week. Your test is due Tuesday. I will not give you an extension on that. It's Monday night, Tuesday morning. It's due before Tuesday. Let's go with that. It's due Monday night. We got to keep moving in this class. We got a lot of stuff to cover still. Digital logic circuits is one of those pieces. It's actually a significant portion of the rest of this course. AC systems is really important. You do need to know it for a number of reasons. So I'm going to be giving you, I haven't yet given you a reading assignment. I was going to give you a reading assignment at the same time as the test. And then I was like, you know what, I'm just going to make sure that you have enough time to do your test. And that's part of why I'm not giving you any extra time. If you want to take your test twice, which you have the ability to do that, you have to get both of your attempts done by Monday night. Okay? There's no exceptions, no extensions there. If you don't hand it in by midnight on Monday, you get a solid 0 on your test. And that is a substantial portion of your grade. Yeah. It's solid when I write it. I'm going to 3D print a 0 and hand it to you. Solid 0. Well, it's better than a liquid 0.
Then I have like a 0 I can put on my desk and show off to everybody.
I got this on my exam. Yeah. Which is more than what you could say if you actually handed in your exam. Yeah. That's terrible. All right, so let's do a little bit of discussion on what we learned last time. So, last time, what we talked about was AC systems. We were continuing our analysis of AC systems. We did discuss a little bit on sine curves, how to add them, how to work with them, phase shift angles. We also talked about amplitude, phase shift angles. Okay, and those are really important to understanding sine curves as a whole. So what we got into last was called complex impedance. And here, what we're able to do is basically represent everything as if it is a quote-unquote resistor. And then what we have for each component is that VL is equal to ZL IL, where ZL is equal to omega L at an angle with a phase angle of 90 degrees. Then you have VC is equal to ZCIC, where ZC is equal to one over omega C at an angle of negative 90 degrees. And then VR is equal to ZRIR, where ZR is equal to R at an angle of 0 degrees. Okay? Because it's in phase. Now, this is what I introduced to you. I did a little bit of derivation to get to this point. I didn't do a whole lot of derivation. A lot of this is covered in your book, which, by the way, you're going to have a reading assignment due over this. So you will have to go into the book and learn it on your own. But that's a piece of what you need to understand in order to get AC circuits. Now we're going to very quickly take this and work on how we can actually solve impedance and in the form of an actual circuit. So before we get into impedances in circuits, we need to understand parallel and series behavior. Because as we've talked about in this class, an impedance in parallel behaves differently from an impedance in series. So here, we actually do, like I said, because the form of this equation, this is a complex phasor form, this form is very similar to Ohm's law. A complex impedance can be thought of as a complex resistance. What we end up doing for parallel series configurations is they sum similar to resistances. Okay, so we're specifically defining these terms in order to be able to add them in the way that a resistance would be added. So what does that mean? Well, it means in series, the complex impedances sum, just sum. Yeah. So here, Z total is equal to Z1 plus Z2 plus Z3 plus whatever, however many components are going to be in series. Okay, in parallel, the complex impedances sum inversely. So once again, just writing out this equation, 1 over Z total is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3 plus ... Okay? Now, the gross piece about this is because this isn't just a number, this is a phasor. 1 over a phasor is super gross. It's not just as nice as like plug it into an equation and then it's like, you got it, man. It's disgusting. So, yeah, I know, right? So I am going to make sure that I'm teaching this right. I always teach this wrong every year.
Oh, that's why I didn't understand.
Yeah. Yeah, welcome to me thinking, unfortunately.
You got this.
Oh, man, I love your positivity here. Because unfortunately, it's complex math, and 1 divided by a complex number, it just goes in a weird direction. Huh? -0. There we go. Yeah, this is part of the reason why I never really get this right. So let's go ahead and just do an example. Here we're going to have Vs. It is a voltage source. And then what we'll do is we'll put a resistor in series with a capacitor. Okay? And once again, the entirety of what we're studying here is steady state behavior. So we're going to assume that this system has been plugged in for long enough that all transient behavior is now gone. We're only dealing with a steady state system because the transient behavior of this system gets kind of gross. And we don't want to have to deal with that when you're just learning this topic. So here, this system can be written as if it is a series of complex impedances. And the reason why is because we have a single Vs source. This is at steady state. And we have a full circuit. So even though I'm going to write this as something, well, I'm going to draw a diagram just kind of because this is how I understand it. Where this is a box, and then this is a box. And then instead of writing R, I'm going to write the impedance, which is R angle 0 degrees. And this one is going to be 1 over omega C angle negative 90 degrees. Okay? So just like what we would see in a regular circuit, we have our KVL and KCL. Okay, for KVL, we know that for all times t, at every point, Vs is going to be equal to Vr plus Vc. Okay? Now, Vs is an oscillating circuit, which means that it may be oscillating between 20 and negative 20, maybe oscillating between 110 and negative 110. There will be times where Vs is 0. And there will be times where Vs is 0 and neither of these are 0. There is still current moving in the system. That's just the nature of an oscillating system. The rest of everything has to sum to whatever this value is at that time. So if it's at a full 110, these two will add to 110. If it's at 0, these two will add to 0. It doesn't necessarily mean that the components themselves are 0, because you can have a current when there's no voltage. It's part of what happens when you get into second order systems. So that's kind of a gross thing to think about. And here, if you do the KCL calculations at the different nodes, what you find is that IS is equal to IR is equal to IC. All of this is identical to what we would have seen in a DC circuit, in a non-oscillating circuit. So the equations really don't change. Okay? Now, what we have that is different is that our component equations are a little different. So as I said, the resistance, ZR, is equal to, it's a phasor of R at an angle of 0 degrees, and ZC is equal to 1 over omega C at an angle of negative 90 degrees. Okay, it's a phasor. We also know that VR is equal to ZR times IR, and we know that VC is equal to ZCIC. Okay? Those are all specific components that we have. All right, any questions leading up to this point? Sorry, Evan, I will move this computer. We don't have to make this harder than it needs to be for you. Did that help at all?
It did.
Okay. It's not gonna, I'm gonna.
As long as you're not erasing and writing the exact same spot right there again.
Let's try to streamline this computer. Make it as thin to your line of sight as possible. Okay. Yeah, so this is where we're at. Okay. What's our next steps? Well, here, our next step is, what we'll do is we'll say, okay, let's calculate what IS is. In order to find IS, you're going to need to do basically what we did with equivalent resistances. And here it's doing equivalent impedances. All right? I'm going to move the camera. It got me like 3 extra feet. Nice. I hate live streaming these lectures because I love using the board just about as much as Levi does. It's like this class is made for using whiteboards, which I can't do in a live stream as well, unless somebody wants to carry the camera around. And no, I don't trust any of you with carrying my camera around. Stop thinking about it. Oh, shut up. You shut up. I wouldn't even trust that. No. I spent way too much money on the camera. But it served a lot of different, very good purposes. So, anyways, what we need to do now is we need to come up with a system equation, okay? And here we have this equation, a VR plus VC. We have these, and we also see that because these add and everything adds, and yeah, that was a good cohesive statement right there. Well done, Kvl. Anyways, now we can basically just plug in our components that we know and go ahead and try to solve this. So here, Vs is equal to Vr plus Vc. Here, I'm picking this equation because we have our driving forcing function is Vs. If I pick that equation, we start with a Vs, we move with a Vs, we already have Vs, we're just missing a Duncan. Okay. Huh?
But there's the not.
There is donut.
We don't need Duncan.
We don't need Duncan. I wouldn't say the whole gang. We got Ivana.
Back road.
What'd you do?
Oh, there it is. I think I have my suspicions for this.
Oh, yeah, I know what Duncan is there.
I don't want to know. Please don't tell me. All right. So what we're working with here is we have this equation. Now, how do we add them? How do we take Vs, which we know what the equation for Vs is? Vs may itself have a phasor attached to it. It might. Vs might be 30 volts with a phase angle of 15 degrees. Okay? That might be what we have. So how do we plug this in and actually solve this? Well, this is where you are going to have to be able to add the complex impedances. So here, let's give some values for R and omega C. Let's say for this system, R is going to be 150 ohms. We'll say C is equal to 1 millifarad, and then we'll say omega is equal to a kilofarad, the most massive capacitor in the world. Kilofarad, yeah. Actually, I've seen a one farad capacitor. It's like this big. It's gigantic. That's why we deal with mostly milli and microfarads. I don't go into pico and nanofarads, but those are very common in circuits because it just gives a little bit of capacitance, but not a whole lot. But I mean, you're dealing with a nanofarad, it's times 10 to the negative 9, and with a picofarad, it's times 10 to the negative 12, and those suck for calculations.
You got like a capacitor that's like an entire acre in there.
That'd be insane. Yeah, because you would need about that in order to, about that much metal plate area to be able to store anything. There's a lot of discussions actually on whether or not supercapacitors can replace batteries. We don't know. We think it's possible, but there's a lot of research into that right now. So what I'm going to do is I'm going to go ahead and replace VR and VC with their respective components. This is ZR IR plus ZC IC. Okay. Well, does that really help us? I mean, sure. If we're trying to solve for Vs here, we know that IR and IC, according to our KCl equation, this is equal to IS. So Vs is equal to ZR IS plus ZC IS. That's pretty easy there. Well, you got to remember again, Vs and Is are phasors. There's an interesting way your book writes them. I am not writing them out right now. But these are not, they're not constant values, they are functions. All of these are functions that are constantly changing with time. So we'll go ahead and add in what ZR and ZC are. And we get, well, I guess we can rearrange this. IS is equal to ZR plus ZC divided by VS. Oh, I didn't write omega. We'll say omega is 100 times 1 over s. Well, it's a 1 over second unit. The angular frequency. Okay, so here we end up with this. All right, that's nice. Let's go ahead and write out what ZR and ZC are. So here this is equal to R angle 0 degrees plus 1 over omega C angle negative 90 degrees divided by 30 angle 15 degrees. Huh?
No.
How do we do that? How do we do any of this? Phasor math. Yeah, that is phasor math, and I'm terrible at phasor math. So let me jump into an example and then steal what they're doing. Oh, yeah, no, it's not as bad as I thought it was. That's right. My bad. Sorry.
Each component drops out, so it's 90.
Yeah, it ends up adding very nicely, which is going to make our lives a lot easier. What we're going to do is we're going to take these and... What did you just do?
I don't even know.
Bro, you're shattering the chairs?
Nothing happened.
I think you might have just ran over your backpack strap.
No, that's definitely reclines a little bit too far now.
Nice.
Could be a pretty improvement though.
It's the same.
Okay, well, I'm just going to keep going. We're going to be able to combine these. So we have talked about adding phasors before. We got to do that now. So let's go ahead and add phasors. So here, R at an angle of 0 degrees. How do we write that?
150 times cosine.
Of 0 degrees, right?
Yeah.
Plus 150 times J sine 0 degrees. Okay, so this becomes 150, because it's a 150 ohm resistor, times cosine 0 degrees plus 150 times J sine 0 degrees. Okay, that is this one component. Yes, 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 that also works. I knew a question you were going to ask when I said yes, because whatever you were about to ask, yes, I'm writing this out in a very stupid way, and there's no need for me to do that. If you want to simplify it because you already understand it, go for it, bro. Okay, and then what is 1 over omega C? So here, omega C is equal to 100 times 0.001, so that's going to be 0.1. It is a millifarad, yeah, that's an M.
What is micro?
Micro is this. Yeah, it's a mu. Kind of looks like an M, just well, depending on how you write it, it looks more like a U. But this, yeah, this is a millifarad because I don't want to deal in big numbers right now. So it becomes a 0.1. So I'm just going to go ahead and write this as 10 because it's 1 over 0.1. So this is 10 cosine 0 degrees plus 10 times j sine 0 degrees. This is 90 degrees, negative 90 degrees. My bad. Okay? So I've just written out the top component, and it's divided by, I'm actually just going to leave this as 30 angle 15 degrees. And there's a reason for that. Because I'm not adding it to anything, I'm not combining it with anything. So then what we do is we combine like terms. First of all, what is the cosine of 0 degrees? It's 1. What is the sine of 0 degrees?
0.
The nice piece about that is that one goes away. What is cosine of negative 90 degrees? What is the sine of negative 90 degrees? It's a negative 1. So I'm going to switch this to a negative sign. Well, no, I'm going to switch it to a negative sign as I go down. So this ends up becoming 150 minus 10j divided by 30 angle 15 degrees. Okay? Adding capacitance and adding resistance, adding inductance, resistance, capacitance, it actually becomes fairly simple because they are perpendicular to each other. So that's kind of nice. I like that, yeah.
Why don't we use the same methods for the 30, 50 degrees?
That's a great question, and I'm going to show you why I didn't even want to go through that effort. We're going to get there though, okay? So I'm going to take this, and I'm going to convert it back into phasor form. Okay? So here, 150 minus 10j, the magnitude of that is equal to, so magnitude is equal to the square root of 150 squared plus 10 squared. Which if I pull out my calculator,
50.33.
On top of it.
150.33.
So the magnitude is 150.33, and then the angle is the inverse tangent of negative 10 over 150.
So it'd be 3.81 with positive values in that.
So that should just be a negative 3.81. Okay, and that's degrees, I assume, because that would make sense. I don't know, you can do that calculation your own. I don't want to. I'm going to go ahead and then just write this now in phasor format. So this is equal to 150.33 at an angle of negative 3.81 degrees divided by 30 at an angle of 15 degrees. Okay, now, you had a great question, Donat. Here's the reason why I didn't simplify this. Here's what we're going to do. To do division, oh, I need more board. I'm going to go over here and erase. I'm out of space, and I'm going to make sure that Evan can't see it. Dang it. I need to turn that computer back. Okay. So when it comes to phasor division, when you have A1 at an angle of B1 divided by A2 at an angle of B2, the equivalent to this, well, that's B2 degrees, I should say, is equal to A1 divided by A2 at an angle of B1 minus B2 degrees. Look at how simple that is. That's why I didn't shift it back. No! Shut up. I'm not going through. The proof is somewhere in the internet, and I don't want to go through it, and I don't even want to talk about this topic. But this is a really nice feature, which basically just means we take 150.33 divided by 30, which this should be something like 5.01. And then that should be at an angle of negative 18.81 degrees. Probably. I just didn't want to go any further out. So the answer is, what is IS? IS is equal to 5.01 at an angle of negative 18.81 degrees. Okay? Now, there's two things we can pull out of this. Number one, what is the maximum value of IS? What's that? I should write this out. IS is equal to 5.01 at an angle of negative 18.81 degrees. Okay, what is the maximum value of IS?
You have to find the magnitude of that.
It is not 150, no, because that's...
Is it the magnitude?
It is the magnitude. Yeah. This is the maximum value of IS. Is there ever a point where there is no current in the circuit? Why do you say yes? Because of the way I asked the question. It's the way I asked the question. Dang you, Jeremy. There is a point where there is no current in the circuit. Why? Because it's oscillating about 0. Okay? So at some points, we're going to have times where there is no current in the circuit, and at some points, we're going to have times where there is no voltage in the circuit because this is an oscillating source. Everything is following a sine curve. Okay? And what we can see now is that by comparison, this is phase shifted about 33 degrees from the voltage. Okay? So it's going to, what that means is that it's actually going to, it's going to reach its peak 33 degrees behind where the voltage is. So here, if I plot out VS, VS is plus 15 degrees, which means it's going to start a little bit up on the sine curve. Meanwhile, the current is minus 33 degrees, which means it's going to show up like this. Okay? Where this distance here is 33 degrees. Okay? That is not to scale, by the way. Does that make sense? That was all that we did. We did all that math just to find that value.
How do you know this 33?
How do I know it's 33 degrees? Because here, this one is plus 15. This one's minus. Yeah, if you take this, well, if you take this minus this, it's 33. So they're just 33 apart.
I didn't see it first.
Yeah, that's fine. It's always good to ask questions. I applaud that. All right, so let's do another example. Oh wait, no, before we get off of this one, let's say we wanted to find VR. We know that VR is equal to ZR IR. So, and we know that that is equal to ZR IS, and we already solved for IS. That's this right here. So if we wanted to know what VR is, we take VR is equal to ZR, which ZR is given as our angle of 0 degrees, which is 150 angle 0 degrees. And then we multiply that by 5.01 at an angle of negative 18.81 degrees. Now, for division, we divided top by bottom, and then subtracted the bottom from the top when it comes to phase angles. How do you think we multiply?
You multiply and add.
You multiply and you add them together. Yes. So here, our VR is going to be in phase with our current. Okay? We know this already from Ohm's law. there is no time lag between your current and your voltage in your resistor. So the voltage across the resistor is going to follow the same phase as your current. It's going to be somewhere up here. Okay. Now, I kind of grossly exaggerated that because I can. It's going to end up being smaller than Vs, of course. But we can take this and then we just multiply them together. So you have 150 multiplied by 5.01, which should be something like 751.5. That doesn't work. That's fantastic. What did we do wrong? Oh, duh. I flipped these two. So really what it ends up being is that we just have to invert this. So it ends up being 1 over 5.01 at an angle of 18.81 degrees. My bad. Just a little mistake, because I friggin' hate this unit. Then we get into digital units, and I love digital circuits. They're just so much more fun. So I would explain why this sucks. So this ends up being 1 over 5.01. So this is 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 equal to approximately 0.2. I'm not going to go do the math. Angle of 18 point. Yeah, makes a lot more sense. All right, so now we go into VR is equal to ZR IR. Here we know that that's equal to ZRIS, as I said before. So then we just plug in here. This is 150 angle 0 times 0.2 angle 18.81. So we multiply, we add, what we end up with is, this is about 30 at an angle of 18.81. It's a little bit more.
Oh, you have just 0.2.
Yeah, it's 0.2.
So it's basically the same as the VS.
It's very much in line with a VS.
Did your like quite a large voltage?
Did your angle change to positive just because of that method?
Yeah, it's because of the presence of the capacitor. The capacitor screws it up.
Then be
Wait, does it?
15 minus 3 point.
Well, it's a -3, so it becomes 15 minus -3.81.
Oh.
Yeah. I'll have to give you another example next class. Which sucks. I friggin' hate this unit. I'm ready for it to be done. Okay. And then to find ZC, we do the same thing, okay? We take 1 over omega C, which ends up being 10. So ZC is equal to, no, VC is equal to ZC IC, which is equal to 10 at an angle of -90 degrees times IC, which is 0.2 at an angle of 18.81. So this is going to be equal to about 2 angle, and we add them together, 71.19 degrees. Okay, so phasor math is actually not that bad once you get to this point.
It's like when you're in like middle school and fractions are scary. They're not actually that hard.
And then when you get them, it's like, that didn't suck nearly as much as I thought it was going to. Yeah, that's pretty much what it's like. All right, I still have you for like 7 more minutes, but I don't think I'm going to be able to complete another example in that time. So we'll go ahead and cover another example on Tuesday, talking about this exact system. We'll go through a simple system, and then we'll be done with AC circuits. We're going to go into digital stuff, okay?
Keep running.
Not gonna no. Naruto running. Impedance.
And that is on.
Dang it!